Good morning. This is April 6th, and we're going to begin the chapter on motion control. And this topic is a topic that will actually allow you to see how to do motion control, both of a stepper and a servo motion single axis. And we look at several applications, and then at the end of this chapter, we talk about actually setting up a single axis motion system complete with the HMI and how to do that and put that all together as a program, both for Allen Bradley and Siemens. And we look at the two, and we realize that there are differences, but they're also very similar in many of the programming aspects. So we ask ourselves, what's the difference between a stepper and a servo? Well, a stepper goes at a discrete angle of movement for each pulse that is given to the controller. And with a servo, it is defined by an analog signal that is output to the motor, and there's a feedback device that says where the actual position is. So it's an analog system as opposed to a pulse system. Steppers are traditionally low torque applications, and they're very inexpensive, and they're open loop, most of them, whereas servos are closed loop and they get to be more expensive, but they also are a lot more torque involved with servo applications. Servo applications and steppers can hold torque at zero speed. In other words, you can hold something against gravity and it will stay at that position until you've over torqued the device. So basically, they will work the same in most applications. Many applications have been using discrete systems, not only with program controllers, but with other devices, and most of the systems that we see today have their background have been developed for a specific application. So some applications fit really well with PLCs, some of them don't. If you have a system that is a CNC system, typically those are not PLC systems, but they interface to a PLC system. So you always have the one PLC system there, but they're not always tied directly to the drives. Some of them are, some of them aren't, and we'll talk a little bit about that later in the chapter. And we have to understand the concept of torque, and its use in this application is that if you don't know the torque of the unit that you're going to be using, you are at a loss, because you must know the torque of the motor that you're going to be using. And it's not a simple application. It usually requires mechanical formulas, and we go through those here. And just as a review, those are the formulas that we have for torque. And we're not going to ask you to memorize these here. We just want you to know that they do exist. And if you are looking at a system, you must ask the idea, is it a closed loop or an open loop system? And where do you apply, if you apply the closed loop, where do you actually apply that? And that's part of these discussions as well. The idea of absolute and relative position. We do have a concept called home, and if you've declared a home in your system, and then you move relative to that, if you say I want to move plus, you move from the home in the positive direction. If you say you want to move minus, you move in the direction away from home in the opposite direction. The difference between relative and absolute is, with relative you move from where you were last as your zero. With absolute, you declare a home position, and that is your zero throughout the whole application. So you declare a home position, and then that is your reference point from there on out. Some applications you cannot do that, and some you can, and we're going to go through some of those here in a little bit. the idea of synchronization between drives. You would have one drive that would be moving in a certain direction, and then the other one would be moving to follow it so that it could then create a unified motion. In other words, you want to do an angular motion, and you must have the one drive following the other drive in order to do that. That's called synchronization of drives. Typically, synchronization requires the coordination between the two drives to be in the sub-1 millisecond time frame. So that's extremely hard to do, and PLCs typically don't do that well. So you have to go to a separate drive unit as opposed to the PLC in order to get that done. The systems, most of them will have a homing switch. The homing switch is located just inside the end of travel on one end of your travel motion. So you have a limit switch that says you cannot go beyond this position to the left or this position to the right, but just inside one or the other there is a homing switch, and that's where your home is established. That's your 0 point. Encoders are your main feedback device, and they usually pulses, and they can be located either at the load or at the motor. So basically you can decide, and you can have more than one encoder as well. If you go through a gear, you might want to do that. Here's applications, and we're going to talk about some of these applications and talk about them. Is this an application that would require synchronization or not? Here's one that probably doesn't, but you have to ask yourself, what is going on here? Well, this conveyor section is a section that can speed up or slow down, and basically lets boxes go onto this next section at a certain distance apart. So the goal is to make these boxes go at a certain distance. So this conveyor can go faster or slower. You really have to ask yourself, first of all, is there slippage between this conveyor and this conveyor? In other words, can you put this box, jam it onto that conveyor? And the answer is probably yes. So that's one question. The other question is, are you able to have a little bit of variability between where the boxes are? In other words, do they have to be exactly X number of inches apart? If that's the case, then probably you do have to have synchronization between your drives, this drive and this drive. Maybe if you didn't have to have exact, you wouldn't have to have that synchronization. So again, all those are questions you would have to ask before you decide whether or not this has to synchronize between this conveyor and this conveyor and that limit switch. So you have to ask all those questions in the process. Here is a blank that's being cut, and you see that the pinch roll is bringing the steel down at a constant speed. This could be steel, that could be paper, but probably steel. You're coming down and crunching down with that cutter. So you ask yourself, how accurate does this have to be? If it has to be really, really, really accurate, then you definitely want synchronization. If it isn't, then you may ask the question, how much can I waste? If I'm going to cut a piece out of this, how much can I waste? And I think that you probably would still want to have synchronization between this drive and this drive. But that said, you may or may not. It's a question you have to ask. This is the same as the last one. Pretty much the same thing. Here we're putting a hat in a box. Now, this one, you have a photo eye and you have another photo eye. So you sense when that next box is going to come in and how far it has to run out, and then you run that hat up there, and then it goes over the edge and goes in the box. How accurate does that have to be? Well, not that accurate, and these drives do not have to be synchronized. This is one of those applications where you can coordinate the axes, but they do not have to be synchronized. It's a good exercise, though, to write a program to do this. This is an application that definitely does require synchronization if you want these boards to have a 90-degree angle. If you don't care, then they don't have to be synchronized. But this is one that you 99 times out of 100 say, yeah, I do want that synchronized. Here's another one. You have to ask the question, what am I doing here? First of all, I'm making plywood. This is a laminate of plywood. I'm cutting off of a log, and I'm pushing that knife into the log, and I'm working at a certain speed. What are my constants? I want to have a constant speed coming down this line. So what happens here, I want to, as the log gets smaller, I want do I want to slow down or do I want to speed up? As I get smaller, I want to speed up the roll, and I want to push this in a little faster because the circumference will get smaller as I go, and it'll have to speed up. This is probably a coordinated axis, unless you really don't care if I have a little bit of dissimilarity. If I'm a little bit shy a little bit or a little bit thicker or whatever on this laminate, I think you probably want to have coordinated axes anyway, but I'm not sure. This is one that's probably coordinated. I would probably make a coordinated axis out of this. You decide. Here's another one. This is like the hat, where you're dropping product into a box. I don't think this is a coordinated axis system. You want to march this box down there. That's one axis. This is another axis. So once you've stopped, then you fill. And I don't think you need to worry about coordinated axis. The really question is a 1/10 of a millisecond, or no, not a 10th, is 10 milliseconds going to hurt you? And the answer here is no, not at all. You got to stop the box, then fill. So a 10 milliseconds not going to make a bit of difference in this application. This is an application that runs these slitters in and out, and they're fixed. So basically, once you run this gear motor in or out and drop these slitters down, let her rip, let her go. This is not something that you would have coordinated axes that would be moving these back and forth. They're going to be constant. These slit distances are going to be the constant throughout, and that's one of the things you have to ask yourself. Is there anything here that 10 milliseconds is going to hurt me one way or the other? No, not at all. Another application using 3 axes, but I pick the piece up, pick it up, move it, and place it down. No. This axis that goes up and then comes back down is not going to make a bit of difference to the axis that moves it down this way. Not at all. So we move the part in. That's this motor right here. We stop it, then we pick it up. We pick it up, we bring it up to a certain height, move it over. That's another motion, and we place it back down. Those are all single axis applications, and they are not critical that the 2 axes have to talk to each other in a sub 1 millisecond time frame. So those are not coordinated. Here's another one that's not coordinated, same as the other one. It's an ASR, automatic storage retrieval system. This one is probably a coordinated axis because you're moving a wire back and forth, or a rope, and you're spooling it up back and forth. This one probably would be coordinated. May not be, but probably is. And this one would definitely not be. This is a shrink wrap system. You don't care if that shrink wrap's a little bit off. It's a system that goes up, or maybe goes up and comes back down, but it's not a system that requires a lot of accuracy. So that gives you some ideas, and we're going to be talking about some actual applications, but here is a application, and I just thought I would throw this in because you're going to be dealing with mechanical components, and we have had some people from this company called Nook, N-O-K, from Cleveland, Ohio, that have actually helped us with some applications, and this is the kind of thing you would ask. You would say, I want an Acme screw for an application, and you'd have to start answering questions. And these are questions that you would ask, and then you would fill those in, and then they would find the right one for you. And so it goes. So basically, they ask you a bunch of questions, and that's where the torque issue comes in, because this is where you would actually be fitting a torque, certain size motor, certain size screw into that application, and there it goes. The method, it's more of a method for how to build a system. This is a review of Chapter 17 on motion, and we're going to go through this, and we're also going to talk about, at the end of the chapter, there is a lab on Siemens 17.1 and Allen Bradley 17.2, and we're going to also talk about the questions at the end of the chapter as well. So this chapter talks about motion in a single axis, and we've already discussed parts of this, talking about the idea of torque, force at an angle, and we've also talked about the idea of building a single axis motion controller, and we've covered this already in our class discussion. And what I want to talk about today is the actual building of a controller and the steps that you would have to go through to do that, and then the looking at the programs as they exist in our trial programs that you would have gotten from the lab, and you would have actually downloaded and added more to in order to make the application do what we're asking you to do. So we're quickly scooting through the first part of the chapter. We've already discussed this part, and we're going down to the part that has to do with the actual implementation of a single axis controller. And first of all, we want to look at the idea of how you develop a faceplate. And this is a sample faceplate, and it would include the idea of, this is for two X's, this would be for an X and a Y, the idea of being able to run a program and stop the program or pause it and then resume. Pause and resume would be the two that you would work together. In some kind of a manual mode, you would want to be able to jog the individual axes, move them independent of each other, being able to present them to a specific point. Obviously, there's an E-stop, and this would almost always be hardwired. This would be something that you would move off of the HMI to a hardwired button, and that would be separate from the HMI screen. Now, down here is the actual the Series 9 programming panel, or the HMI panel from Allen Bradley. So in their this was back about year 2000, they were selling the Series 9 single axis or two axis speed control, and they would basically sell you this as a panel that would go with your system. And there's half of it, here's the other half, and that physical panel was hardwired back to the controller. So we're asking you to do something a little bit different from that, but on the other hand, that's the starting point. Now, with the stepper controller, we have tried various things, and at the beginning, when we first bought the earlier version of the Allen Bradley and the Siemens processor, I knew that the Siemens processor, because I'd gone to a little school on it, could handle what you'd call a stepper output, and it's the a pulsed output, PTO, pulse timed output, that would basically give you the ability to the number of pulses gave you the speed, and if you pulsed, it meant you moved a certain angle of the shaft. So I had tried to put this together with on a breadboard using an L6208 chip, and I was kind of ahead of the curve as far as the Arduino. The Arduino now has the capability of, with the shields that they have, of doing the same thing, but this was prior to when we bought this block, this card. This was prior to the introduction of the Arduino, or at least it hadn't hit in Toledo. So we went ahead and bought this little control block, and it was, I burned up several chips just trying to match up all these resistors and do this on a breadboard. So I finally just said, okay, this is a $30 controller, and it would work with the output of the Siemens, and that would be how we would move a stepper motor. So basically, the stepper motor receives pulses from this card, which receive pulses from the Siemens output controller. So that's how that's done. And we would use the motor control blocks from the Siemens Corporation for their controls. So basically, it's an open loop system. We control a little stepper motor like this, and we basically turn the shaft, and we just notice when it's in a certain position. So basically, so many pulses would turn one revolution of that shaft, and that's all we were doing. And that's how this is wired. And if you look at this, this is that controller, and there's some interface going right here, and we have it set up so you basically see a little screw on that shaft, and it would turn the shaft so much. And the power supply back here was for the 12 volts to power up the stepper through that card. So there's the 5 volts, the 24 volts, and the 12 volts, all to make this thing run. So the 5 volts were the control signals, the 12 volts was the power for the stepper, and the 24 volts is to basically control the PLC, the output of the PLC. So you got all those voltages running, and this is the processor, the way it was done, and we basically would set that up and take the program from it. And we've gradually gotten away from the 12 volts, setting it up on the on this little power supply, but that's one way of doing it. And it looks like a mess, it looks like a rat's nest, but it works. And we are able to turn a shaft based on this. Now we also added these little switch terminals based on the idea that we were using them to initialize various inputs. So there were no inputs in our program. We were using the HMI as an interface. So basically these were to do various inputs to try various functions prior to using the HMI. So this would be, for testing purposes, we would use these switches, and that was why they're useful. This is the HMI that you would have created. Okay, so we now get into the programming aspect of it, and you would basically create all these commands, and we're going to go through these commands, but these are from the you would drag these in from over on the right hand side of the page, and basically under motion control you get all these different devices. And you would notice that you have various commands, like you could halt, you could home, and you could do absolute moves, and you could do relative moves, and you could just have a move velocity, which was nothing more than a continuous move at a certain velocity. And you could turn the power on, and you could also reset it. So basically the power always had to be on, and you could do a command table, but we decided we were going to get fancier than a command table. A command table basically allows you to move through a series of commands, but there cannot be interrupted. You cannot pause them and resubmit and restart them from that point on. So I wanted to make a little bit more than just enter a bunch of commands in the command table. So I asked you to do something a little bit more sophisticated than the command table. Although I imagine most of you would start with a command table and then move on from there, but it's not the ideal. So you would also create an axis, and you would get all these under the axis configuration. You would get all these various points, and we would be able to create that as well. Okay, so now we need to look at the different types of homing, and one of them is active homing, and one of them is passive homing. Okay, and active homing, you would approach a point, and you would actively go back and forth over that point until you got it homed. Passive, you don't carry out any motion control. So basically, but you would still establish a zero. So this establishing a zero, or an absolute point where you would say this is my 0 point and everything to the right of it is plus, everything to the left of it is minus. Either approach gives you the ability to do absolute moves. So either way gives you the ability to do that. We're going to do passive homing because we don't have a switch that we would call a homing switch. Okay, so these are the steps to create a program for the processor, and here we're looking at some of these various steps. Now I'm going to go down here and just go through some of this. There's a bunch of to create a technology object, you have to go through all these steps, and you have to define an axis, and here's some of the steps in defining an axis, and you would have to do these. Now here is the critical one: pulses per revolution, and that would be 200. So if you say I want to go around one time, you would enter in the number 200, and that would be an absolute move. If you were at 0, you would go 200 moves, and that would go 1 revolution to the right. If you wanted to say you were at 0 and you wanted to go 400, it would be 2 revolutions to the right. If you said minus 200, it would be 1 revolution to the left. If you were at 200, in other words, if you'd already moved 1 position to the right, and you wanted to go to 400, you would say 400, and it would move you from 200 to 400 if you had an absolute move. So basically it would just do 1 more revolution. So that's the key, is that number. And Allen Bradley and Siemens both have a number, and they're both have programmability for that number. So basically you got to remember the number for the Siemens is 200, and for Allen Bradley it's 360. Now when you program these steps here, you notice that you have to go off of 0, because 0 is not a valid speed, and you have to program in an acceleration time, a speed, a maximum velocity, and a deceleration. So you have to program these variables in. Now this is something that you just have to try if it's not already recommended, if there's not something already recommended. Fortunately for you, they've already been implemented, and these numbers are already in there, and they work. If you did not have a working system, all these numbers would have to be implemented by you, and you'd either follow somebody else's directive, or if it's for a specific motor, many of the motors have a recommended accel, decel, and maximum velocity rating. So again, those are settings that you have to set up. Those are already set up in the system for you, and you don't have to worry about it. This has to do with the idea of going. This is extended parameters. From approaching a reference point from the positive or the negative side. This is describing homing, how you would home. So you go around it, you go back and forth until you hit it a couple, 3 times, and then you would know that you've gotten to the exact point. This is the idea of describing a motion and then another one, or a blended motion. And we do not have any blended motions here. We just have this kind right here, but if you wanted to do blended, you could. Okay, so the commissioning of the axis, you would set it to automatic, and you go through all these steps, and you would basically just control it until you got it to run, and make sure that it runs in the positive direction, make sure it runs in the negative direction, and these are all settings that you would have to put in. So again, not trying to make this more complicated than it already is, but this is what you would have had to have done if you'd have started from scratch. That's why these are very complicated instructions, and that's why it takes time to develop these. Okay, so anyway, moving along. Okay, so these are the instructions as you see them when you first get your program, or when you first get your program. Now you notice this one says reset. So if I want to reset my axis, I look at this right here and it says I0.0. That would be the switch that would reset that axis. In other words, if it's gotten messed up or something or other, I would turn that bit, which is the first switch bit. You remember we showed you those switches? That would be the first one on the left. It would go up and go back down, and that would reset it. This is power, I0.1. So you would turn this one on and leave it on. Home, this is the I0.2. This is the third switch in, and you would say, okay, I want to declare that position as a home, whatever that position was. If it was straight up, then you would say, I want that, and then I would declare that as my home position. Move velocity, I0.3. If you turn that switch on, it runs at a specified velocity. Here is 200. That's just a number. But basically, it's a certain speed, and you would see the axis turning at that speed, and it's going to stay. It's going to continue to turn until you halt or reset the drive. So that's a position like that. Move relative is a distance at a velocity, and this would be the number. This would be a quarter of a revolution, and there's your velocity. So basically, that one is a two settings, distance and velocity. So this would be a quarter of a turn from where you're at that velocity of 10. It's a slow move. Here's the halt. This would halt. This would be used to halt if you were just letting it run, and that would be to stop the drive. Absolute move, which is what we're going to use the majority of the time, is a position and a velocity, and this is an absolute position. So if we're already at position 50, this would not do anything. If we're at position 0, it would move 50. If it were position minus 50, it would move 100. It depends on where you're at when you start. And this would be the speed. It's a little faster. This is the Allen-Bradley instructions. Same thing, same kind of thing. And this is the Allen-Bradley system. It's a more expensive system. Here is the little dial, and the servo motor is right in back of that. And here's the controller for it. And the servo motor is relatively small. The controller of it is not that small, but it runs out of this program controller. It's a little bit more sophisticated program controller. It has to be this, or it has to be at least of this style, and it's more sophisticated than the one we have. This is a picture of a bigger version of the servo motor. Here's the power connections, the controller connections, and there's your shaft. Here's the back side of the controller. There's the encoder. Here is a picture of the shaft taken off, and here is these are magnets, and these are positioned so that the field and the armature are reversed on a servo motor. So the up in this potted area are is what's the armature, which is the electrical part that actually switches and turns it to hold these magnets in a specific position, or it gives it a speed. Again, this is the commissioning portion of the Allen-Bradley. The Allen-Bradley does not have the switches on the top like the Siemens does. So the little switches that you have for commissioning are not on this one. but this one is specific to a motor, and you buy the motor and you get all you get all the files with that motor, and that's what gives you these the things to put in these various commissioning tables. So again, we have both. We have a servo from Allen Bradley. We have a stepper from Siemens. But basically, they're doing the same basic thing, which is controlling either absolute or relative to a position, and you're moving a single axis to a position. Okay, so we come down here, get through all this. All this commissioning stuff is important, and I printed it out because I wanted you to see it, but it's not where we're at because we've breezed through this part of it. So again, you're required to do all this, but we've already done it for you. The two look very similar when you get down to it. The main difference between the two is that Siemens does not require you to have a specific tag for each motion, whereas Allen Bradley does, and I'm going to show that to you here in a minute. You notice that the Allen Bradley has a tag that we call it a motion control tag that goes with each of these actions. So we move through various tags, and the way that you get access to this information is through this tag, the .en, the .dn, or the .er, which is the error. If this one doesn't work, it would give you an error. And this would be jog, motion axis jog, MAJ. And here are the output bits, which would go with the tag mctags_4.er.ip.dn.en. So that's how you get access to the things that are in this block. Again, this was written kind of as a starter program, but the point is this: with this one, there's no I's, there's no input, so you cannot get an input directly, a switch input. But what you can do here is you can right click and toggle that bit, and that'll execute that instruction. So that's how you would test each of these functions. All right, now this one also has a command table, which we're not going to use, but you could use if you wanted to, if you're developing. And this was something that we found, but I would not take seriously now. This is something that is not used anymore. Okay, so we come down here and we're going to skip through this part. We may come back to it later, but as of right now, we're going to come down here. So now we begin with the portion on the actual starting and stopping of the Siemens program in the test mode. So basically, I created a state diagram of the motion application and give you a description of how to move forward with it and try to go in the auto mode or in the manual mode, which I want you to be able to do, and understand the various aspects of how you can make the motor do a stepwise motion and return back to its home position. So basically, we're assuming that you've already gone through and you have homed that you started the motor and you've homed it in order to get to this point. So we know that we have an absolute position, and you can either choose to go in the auto mode or you go in the manual mode. So you have a selector switch that you can pick which way you want to go, and then you can, if you push the start button for the auto mode, it'll go through a sequence of 3 steps. First one is to move forward, and I don't care how many revolutions you go forward. You can go 1 revolution forward, you can go 2 revolutions forward, you can go 10 revolutions forward. It doesn't really matter to me. But then you stop and you dwell for a little while. That's a timer. And then you move backwards through that. You come back and you repeat, go back to the initial home position. So basically, you go out, you go maybe 2 times forward, 2 revolutions forward, stop and dwell for maybe 5 seconds, and then move back the 2 revolutions back to your home position. The key to this is if I hit halt anywhere in here, and I could hit halt here as well in the dwell, but I have to, if I hit halt in this position, I stop immediately. I enable the halt block to work, and it stops me dead where I'm at. And then when I hit resume, it continues in the forward direction. Now this addition to the basic stepping program makes it so that I cannot use the command table. So I have to program this in the blocks, and I cannot just use a command table, either the Allen Bradley or the Siemens. So again, here and here, if I hit halt, I have to then resume from where I'm at and finish the action. And that's why it's very important that I use absolute control, because let's say I stop at 150, the 0.150. All I have to do is say go to position 200, let's say, or maybe 400 if I'm going 2 revolutions, and it would finish that revolution off. It wouldn't have to know where I'm at and then calculate for me. It just says go to that finished position, and then it would move to here, and it would move to here. So how do you do that? Well, you have to do it through the idea of some kind of a stepping program, and that's what I provided down here. Now, under here is the sequence of how to. You can either do this manually, or you could do it manually. You could set up a program to do this. As far as I'm concerned, you can just, with the Siemens especially, you just have to do this with these switches. So basically up here with the switches, they're all down. Then the second one would turn on. Then the first one would turn on and back off. And then the last one would be and leave the second one here on. And then the third one, then you would go up and back down. And that would home. This would create your homing. So basically, this is the initialization portion of your program, which is what we call up here your initialization right here, initialize, and that's what would be done in that program right there. So you do that by hand if you want to. That's one way of doing it. So here are the blocks, and here is the switches, and you just leave them alone, and then that's all you have to do. Now down here we start with adding of some more information, and I actually added some programming down here that actually allows us to move through these steps. So here is the program. It's a partial program for the state diagram. So basically what you do here is, I've written this out. If you were to copy this over, you could get this thing to run. So you have a switch that you would either set to auto or to manual, and this would be tied to an indicator button on the HMI screen. And if I'm in auto and I hit start, and I'm in step 0, which means I haven't started yet, I would put a 1 in my step, and that means I'm starting now step 1, and I would move the number 400 to my position, which basically says go 2 revolutions. That's go twice around. So that gives me an initialization, and then also when I'm in step 1, it sends a pulse down here to the move 1, which is a pulsed input, and that says start this guy. And in other words, that goes to my program down here, but initialize the move to position 1. And it gives me both the length and also the pulse to say start. So this would be, this from all the different positions, this would be my IMS 3.0. This would be one of the things that contribute to 3.0. And this would be my position. Okay. So this is the absolute move block, the block that I would execute from a number of sources to give me the ability to move, and then also how far to move or where to move. So here is my start, and it would come from either the input, which would be the tag, the selector switch, the resume bit, or the move to position 1, or move to position 2. So basically these are all the things that can contribute to this bit up here, are these various bits down here. So again, these are the ones that any of these pulse bits can contribute to do this executing of this absolute move. So this needs a pulse to say do it, and that's what you do. You basically give it an input, leading edge, and away it goes. Okay, so when I am in position 1 and I am done, it moves to position 2, which basically says what? Wait a little bit. Wait a while, whatever that time is, but there's some time in there, and this says 2 seconds. So basically this one's set up for 2 seconds. You could set it up for as long as you want. Then once you're done with 2, it moves to position 3, and it gives you a new position, which is position 0. So I'm moving from position 400 back to position 0, which means I go back and retrace my steps, go in reverse for 2 revolutions. And then when I'm done with that, I end it and I put a 0 in the word step, and I'm done. So that gives me a starting point. And here's the jog. This would be getting us to moving forward. This would be a different velocity, and you could move it as fast as you want to, but usually jog is a slow move. So this logic handles the slow move, and then I do that move, and then I also have a halt. I have a move velocity, and I have a halt, which basically says stop, and I do that. So basically this is the one is a forward, one of them looks like it's a reverse. And anyway, this is the jog commands. Here's my halt command right here, and these are the things that can make it halt. So again, if you were to put this program together with an HMI screen, you probably would be able to very quickly get it to work, and you could try this out and set it up, and it's gonna kick in and it's gonna work for you. So that is the basic setup for the Siemens program. Okay, so here is the this is the so this has been adding the home action, which is basically establishing of the home. So I added a little bit in this one to actually add that function to the state diagram. So I have to return to home here, or there I have to establish a home. So when I come into the stepping forward, I have to return to home if I'm not there. So again, that's another step you might have to add. Okay, and this is not in your program, and you need to add that to your program if you're going to write this one and turn this one in. So again, with the kinetics programming panel, this is the same identical type of program for the Allen Bradley, but with the Allen Bradley, the difference is, and I'm just going to go through this really quickly. The difference is how do you get to a position, and I'm just going to show you. Whereas the Siemens one, if you're done, the done bit comes on. So if I do a specific action and it's done, the done bit comes on. Here, there's no move velocity, but basically, if I tell a move absolute, the move is done right there. But with Siemens, with Allen Bradley, it's not the case. Allen Bradley has a variety of bits, and I'm going to go back up here and I'm going to show you those bits in a second. And some of those bits are rather deceiving, because the done bit doesn't mean you're done. It just means that you are to a that it acknowledges that it started doing the action. The IP means it's in progress, and PC means that it's complete. So if you said mctags_5.pc, that means that this motion axis move is complete. The .done bit does not tell you that. It just says, I'm doing it. I've accepted your command, and I'm working. The in progress turns on at that point in time, and when it's complete, it'll turn on the this. And the move type, there's two different types. I think one is is relative and two is absolute, or vice versa. But basically, you put in the type you want here, and that's 0 or 1 or 1 or 2. I forget exactly, but the move absolute, move relative is handled by a number in the move type word. So basically, you can do the same kind of program with Allen Bradley as you do with Siemens, but instead of the done bit, you take the .pc bit, and it's off of this tag. And other than that, the programs are the same, and they do the exact same thing. This has feedback. Obviously, it has it's a servo, and it has feedback control, and you will hear it humming when it is in its working mode. Even though it may not be moving, it'll be as I say, it's motoring, even though it's at 0 speed, and you'll hear it hum. If you don't hear that hum, it's not going to take off and run for you. So it has to be, that is the enable bit, and it is either enabled or it's not. And if it's not enabled, you do not hear the hum. If you do hear the hum, it is enabled and it's ready to go. So listen for that when you're doing the servo motor. It is not the same. You don't hear anything with the Allen Bradley, or with the Siemens, the stepper. You do not hear a hum, but you would if you would. The servo gives you the hum. It's not the Allen Bradley or the Siemens. It's the servo versus the stepper that gives you the hum. Okay, so that gives you the ability to write those two applications, and that's something that we ask that you would be writing those two applications, at least filling in as best you can. I know you can't run it, but to write it down and send that in would be the main goal of the last part of this, the assignment for chapter 17. Also, in this chapter, we would like you to look at beyond the single axis, and what would we expect from a multi-axis machine here. Well, I do have some examples of multi-axis, and I'm going to try to find them here real quickly if I can. This is a multi-axis controller that's put in an Allen Bradley processor, and this is an article on that. And this down here is a card that is used by Allen Bradley. This is what we call a third-party card. It's by a company called AMCI, and it has two axes. And basically what you want to know here is what are the commands that you can use that would actually allow you to run multi-axis machines. And they're rather simple, so that you can control along the x-axis or the y-axis, or you can control a line that is at an angle, and you can actually run two axes that actually draw a line. If you wanted to do that, you can. So what other kind of things can you do? Well, you can actually look at circles, you can look at arcs, you can go in an arc, and they have different methods for programming that. And that's about all this one does. There's three different approaches to programming an arc, but you can program either in any way, in any one of those formats that you want. But basically, arcs, complete circles, and lines in any direction are your only option with this language. More sophisticated languages include things kind of like G codes. G-code is what you'd run into in a machine tool system like a lathe or a milling machine. And this would be a coding system that utilizes multi-axis and tools to be able to control a cutting action along a line or in a circle or in a some kind of a motion in a 3-axis machine. So basically, the G-code and M codes, basically G-codes give you that capability. And if you've never seen these, this would be what you would see in a machine tool application would be the G-codes. So that's more sophisticated than any of the 2-axis systems that we presently are talking about, or the single axis that we're presently talking about. And then this would be an article on 61133-3, which would be a PLC, and there is movement to incorporate the basic languages of motion with the PLC languages. That said, there are so many of these that it's hard to describe exactly which one's going to win out, but there's an article on that as well. Okay. So that gives you a little bit of an idea about single axis motion, how you would move from single axis to multi-axis motion, and then how you would even go to the more sophisticated M-code and G-code systems. And then we have some applications down here at the end, and we have some questions that have appeared on tests before, and I want you to know that if you want to, you can submit some of these answers for extra credit as well. So you come down here and you can answer some of these questions if you so choose. But basically, they are at the end of this chapter, and any of these questions that you want to tackle, you certainly can. These are questions that have appeared on tests, like number 11, number 12, number 13, and number 14. That would be one that I've actually asked on a test before, and you may certainly ask those questions at your leisure. Take care. We're picking up here now with the HMI panel, and this would be a typical HMI panel for a machine tool application with 2 axes, and these would be soft buttons. Now down below I show the same basic application with actual wired buttons, so you could see either type of application, and sometimes the soft buttons are okay and sometimes they're not okay. But one of the buttons here that we would probably not want to use would be the e-stop button, which is at the upper left. You don't want to use that as a software button. You want to hardwire that so that it would effectively stop everything. And so that would be a warning about this panel. If you want to use this panel, you could, or ideas from this panel to build an application, but you should always use the e-stop with hardwired logic. This is a part of a panel from Allen Bradley, a Series 9 panel, and this was back about 20 years ago that they were selling these. But this would be for a system with multiple axes, maybe a lathe, maybe a milling machine, but the controls for that machine would be something like what you would see right here. And these are all hardwired buttons, and the pots are real live pots, and you would turn these knobs and you would vary the voltage. So that's a little bit different, but it's the same kind of idea. Here's the other half of the one from Allen Bradley. It would be a long, narrow HMI, but you would see the buttons that would be used would be this kind of button. So again, you have some choices here, but you're going to have to build an HMI panel, a simple HMI panel, with any of the applications that you would build, and you just need to consider the actions that you want and whether or not you could put them on an HMI, or you have to put them on potentiometers. And I sometimes think potentiometers are probably the best way to go. You have to decide. So we're down to looking at both stepper and servo controls, and we've gone through a lot of evolutionary processes in the steps to getting a successful application with either the stepper or the servo. We started with trying to build a stepper controller from chips, and that was not a success. I successfully burnt. The only thing I was successful at was burning up some of these 6208 chips, and finally gave up on that and went to a board, and this was the board that we found, and it's about a $30 board. There's nothing wrong with this, but this was kind of pre-Arduino days, and now the Arduinos have kind of taken over, and most of the applications that you would see would be a shield that would go on an Arduino. So even though there's a lot of different ways of going, but basically the Arduino has given us impetus to use devices that would go with it, and also the 3D printing has given us impetus to use some of the simple stepper drives from 3D printing area, and that's what we're tending to go toward now. And as you look at the lab book, chapters 18, 19, and 20 show the various stepper and servo applications that we have, and we're talking about chapters 18 and 20 in this text. But chapter 19 is a new chapter, and it features a board that does not. It's about $20, and everything that you would need to run a single axis of a stepper is from a programmable controller, from a Siemens programmable controller, is just this single card and the stepper itself and some resistors in the middle. So it's an evolving process, and today we're into going with more sophisticated but cheaper drive boards. So this would be one that you could use. There's nothing wrong with it. The only thing that you need to remember is you have to there's a 12-volt supply, a 24-volt supply, and a 5-volt supply, and you have to use all three of them in order to get this thing to work. And here's typically what you would have as a system. This would be the way it would be set up in the lab, and if I can get a picture of it here, this is the servo motor itself, and here would be the eval card, and here are some other terminal strips. Here's a lot of wiring, and then here are two cards or little voltage converters that you would have to use as well. Now these are sitting there. Now these are not cheap, but I wanted to show you some of the things that can actually be done in programming of a system, because many times you would be tempted to come up with a device yourself, or maybe some chips, and put them on a board and solder them. And these are not that. They're already pre-done, and I would recommend them highly, because most of the time if there's something that can go wrong in a panel, they point to the things that have been done by hand, the solder jobs or whatever, and the specialty boards, and those are the things that, even though they might not have anything to do with it, they may actually be the ones that people would criticize. So this would be the Siemens PLC. The output would be the direction and the clock pulse, and those are all tagged together, and they work very well. Here's your 12 volts. You have to have 12 volts for the stepper. In this case, not in the other one. The other one with the newer equipment, you can use 24 volts. But this one, the eval board, this thing right here requires 12 volts. So again, not quite as simple, but it works. So here would be the PLC, and these switches are referred to in the program. And we leave those on because they're very handy ways of starting and initializing our system. And instead of having it on an HMI panel, you can just flip these switches and you can try your system out. The goal of each of these systems is to get something to run. If you can get the axis to turn, then the rest of it, while it's not trivial, isn't that hard. But getting it to run is a key part in all these. And here is an HMI panel, although today we're encouraging you to not use the HMI, but to use the the simulated panel on the computer screen. So basically, at that time we were setting up, when we first started, we were setting up everything to run off of the Hmi panel. Not so today, and we're not going to worry about that. Okay, so here's the basic program in the Siemens for the stepper, and you notice that we have called in all these program system blocks, and these are all used in our program. So basically, these would be program blocks that you would incorporate to make the system run. We already have a working system, and you can download the system with the base system, and then you can modify it and make it run. But all this stuff has already been built for you. The good news is you've already got all this stuff in this system, and all you have to do is get it, use these in the switches and get it to run. Now, if you find that you have a different version, a different version of the software, if you were going from version 11 to version 13 to version 14 or version 16, that's easy to do because it'll just upgrade to the next version. If you're actually moving from one processor to another processor, a 1214 to a 1215, then you have to, in a case like this, you can't just copy paste the various parts over because there's too many of them. So here you would have to actually create another application, and you'd use the help screens that are at the end of chapter 19 for that. I believe it's chapter 19. But those are there, so you can we'll discuss those later. But anyway, so we're talking about different types of modes, and you have active homing and you have passive homing, and we have a passive homing system that you flip the switch that I showed you, those little toggle switches, and that gives you your home position. Wherever you set that, and then you flip that switch, that homes your system. So that would be one of the first things you end up doing. Okay, so this goes down through and says get how to get started in opening a motion control system. This has already been done for you, by the way, in both the Allen Bradley and the Siemens, so you don't have to worry about going through these, but this has already been tackled. Thankfully, you don't have to do this. Okay, so we're going to go through this in kind of in a hurry, but not too much of a hurry. But want you to understand that this part would maybe take you a day or two or three or four or five, and we want you to get at least to the point where you can move an axis. That's the key, is moving an axis. And here are all the parts for setting this axis up, and you would have to set all these parts and pieces up yourself. Again, this is all done for you already. And then both on the Allen Bradley and the Siemens. This is the homing operation if you had a homing limit switch. Now the commissioning part of it, it goes through and talks about the commissioning, but again, this has already been done for you. The thing I'm looking for here is the number of pulses that you need to go one time around. And I believe that's one of the variables that is entered in here, and I'm going to find it here in a second, hopefully. So for the Siemens, if you pulse it 360 times, it should go around one revolution for 360 pulses. So if you say
move forward or move 360, it will move 1 revolution. If you say move 720, it will move 2 revolutions. If you say move another percentage of 360, it'll move that number of revolutions. So that's key to the stepper, is 360. For the Allen Bradley servo, I think it's 200, so you need those numbers when you say move. If I want to move 200 in Allen Bradley, it would go 1 time around. If you say move 400, it would go 2 times around. If you say move to 0, if it's an absolute move, it would be back to home or back to 0. So again, that's information that you need, and that's pivotal in being able to program your application. So those are the only 2 actual things you need. Again, the commissioning has already been done, and you can use this application. You can use this as a starting point. You do need to be able to know how to the order in which to flip those switches, and we'll talk about that in a minute. So these are your instructions, the various instructions you have, and these are the motion control application helps. I'll give you some ideas how to check some of this stuff out. These are on the help screens. Okay, so these are the program that you're going to get, and this is the program you're going to get handed to you. And as you notice, this is the reset block, and it is tied to I0.0, which is that first switch. So the first thing you're going to do is, when you power up, you download this program, then you're going to flip that switch up and down. It's going to go on and off. So you reset this by just flipping that switch on and off. That will reset the drive. The second switch is the I0.1. Then you're going to flip the power up, and it's going to turn the power on. That's your enable. So with the servo, when you hear enable, it actually starts to hum. With the stepper, you don't hear anything, but it is now enabled. So it basically it's a nothing burger from the stepper, but from the servo, the Allen Bradley servo, you actually hear a visible hum. It's enabled, and it's holding position at that point in time, so it's working. I0.2 is the third switch, and it is your homing switch. So you position the dial on the end of the shaft to wherever you want home to be, if it's straight up and down, or if it's 90 degrees off of that, or whatever, 180 degrees off of it, or whatever it is. You flip that third switch up and down, I0.2, and that declares that as absolute home. So that is your homing switch right there. That's your that's how it's homed. And for the fourth switch, I0.3, if you give it a velocity here and flip that switch up, it will move. It should just move at a steady velocity. That's not moving to a position, but it's moving with a steady velocity. And that's how I would test to see if the drive is actually working. After you've done those first 3 switches, this is the fourth switch. Give it a velocity. 200 is fine. Flip that switch up. If it doesn't take off, you got something wrong. If it does take off, it's a good sign you're on your way. Move relative is I0.4, and halt is I0.7. So you can move relative, you can move and then you can move absolute, which is I0.6. I0.6 is the one you're going to use, because I'm asking you to go forward and then come back. So basically, it's a absolute move is your best way to do that. Okay, so and I'm asking you to be able to do a jog in there as well. So this would give you the ability to know where you're at all times. The same with the Kinetics 350 single axis servo drive. Very straightforward. Does the same basic things, except with Allen Bradley, you do not have the little switches. That's okay. We can live with that, because I show you that these switches, they're not, you don't actually need. Now this is your servo drive, this is your servo motor, and there it is broken down and looking inside of it, and there's your encoder in the back. There are the permanent magnets in the armature, and the field has the excitation coils that actually would attract or not attract these permanent magnets. So this gives you a look at some of the screens for the Allen Bradley. Again, we give you a program. It's not a finished program, but it gets you started. And this would give you a look at the screens that you would have had to configure and go through and configure. These are the things we had to do in order to get the Allen Bradley to work. There's a lot of screens, and that's one of the problems with drives, is they take a little bit of time. And if you're in a hurry, or if you're under a gun, if you're under a lot of pressure, sometimes these can be very hard to get up and running in a short period of time. It says 360 degrees per 1 revolution. I don't know if that's I thought it was 200. Maybe it's 360. Try both and see which one is which. One is 200 and one is 360. There's a lot of parameters. As you can tell. Okay, so both of these have what we call a sequencer table, but you cannot use for either of those. You can't use it. Now here is the test program for the Allen Bradley. So you would have to toggle this bit. Toggle it on, it resets the group. Toggle this, it turns the motion on, and you'll hear it hum. This is your enable. This is your servo off. You don't want that. This would be your jog, which would be toggle that, and it should move. This would be stop, so you could stop with this one. Motion axis move, and this would be move type. I think 0 is either relative or absolute, and the other one would be 1, so you'd have to check which one is which. I think it's in the literature. I forgot which one it is right now. And that's really all you need for this one. Okay. Now this is a picture of this table, and like I said, it's possible that you could get this to run, but we were never able to get it to run, and I would recommend that you not spend a lot of time with it. This should come out, but it was something that we felt at one time that we needed. You can ignore it. This is a letter about single axis control, and we can ignore that as well. And this would be a multi-axis system. So this would be a multi-axis, from an Allen Bradley point of view, a 2-axis stepper system or servo control system. And they talk about the language for it, and they talk about the control of it for 2-axis stepper. And it's interesting to note some of their languages. Basically all you can do is you can draw a straight line, or you can draw a part of a circle, or you can draw a whole circle. You can draw an arc of a circle, or you can draw a whole circle, and they talk about how that's done. We're not interested necessarily, but just to note that it's there. And if you get into more sophisticated systems, you might find stuff called G-code. And that G-code is a language that is used by people who are doing milling machines, lathes, that type of thing, all kinds of metal cutting machines. And this is what G-code looks like. Okay. So now we have the lab, and here is the statement of the lab, and what is wrong with being able to use those little pictorial and the graphs. Well, I make you have to start and stop. In other words, I'll make you halt and then resume, and those programs do not allow you to do that. So here's the state diagram for a simple machine, and I want you to be able to rotate forward, dwell a little bit, start, stop, time it, and then come back to the home position. I don't care whether you go 2 revolutions, 3 revolutions, 10 revolutions, 100 revolutions, but I want you to go forward, stop, and then come back. Now I also want you to be able to halt, and then when I hit resume, it goes back and continues from that point on and continues down the road. I also want you to be able to go to manual mode and be able to jog forward and jog reverse. Okay, so with the Siemens, you use these switches, and I outline the steps to doing the switches. First, they're all down, then put the second one up, which is the power, then I toggle the first one on and off, which is the reset, then I toggle the third one on and off, which is the home, and these are the instructions that I see that you would have. And then once I do that, I go and I toggle the move or the relative move, whichever one you pick, and it should take off and run. So that gives you a little bit of a heads up as to what to expect. You need to know the absolute move instruction because that's the one you're going to use. And that gets you an idea about how that's done. This is a potential screen for you. That might be something that you might consider. And here's a program that might actually work. If you enter it in, it might be doable. You might find this might be helpful, you might not, but it's something that you might look at. Okay, now that's for the program for the stepper 18 using the eval board, and also for the one in 20, which is the newer card as well with the stepper. Both of them work off of the same program. Okay, they both work off of the same program. But when I'm talking about the one in chapter 18 of the lab book or chapter 20 of the lab book, those are the two. Now here is adding a return homing action to establish home after you switch modes. So you may have to consider doing that. That was added. And the 17.2 is doing the same thing, but with Allen Bradley instead of Siemens. So you rotate forward, you rotate back, and see if you can get it to work. And this gives you some of the ideas of the motion application instructions. And so it gives you a little bit of an idea about some of those applications. Okay. All right, executing instructions. The one thing you have to be careful about with Allen Bradley is that the done bit is not the it carries through that you have 4 or 5 outputs, and one of them is a that you're done with the instruction. The other one is that you've actually reached your final destination. So that's the one you want to use to go to the next application, to the next screen. Okay, so this is some of the problems in the chapter. None of these are that difficult, so I'm just going to let you go through and see if you can work them. This one obviously is a fast. This would be a deceleration. This would be a slow, and that would be a moderate speed for a stepper. This would be a simple program that you would use, and there's a lot of different ways of doing this, but you would move the boxes up to a specific point, and then you would move the hat and drop the hat into the box. Okay, so I want to go back and I want to show you chapter 10. Excuse me, chapter. I want to show you the chapter in the book that has to do with the new in the new stepper. So hang on, we're going to go there. Okay, so this is the new stepper motor. And this is from chapter 19. So it's chapter 18 is the eval board, chapter 19 is the stepper, and then chapter 20 is the is a rehash of the servo motor. So you can use those if you want to, but really they're the same as in this chapter. But this is not. This is a new. Chapter 19 is a new approach to doing the stepper motor application. So here we have the full kit, and it is a simple little kit from the robot shop, and you would use these commands like are in our chapter, and you would use these instructions, and you would set it up just like we did before, and you would wire it like they did right here, which is instead of the MCU, which is a microcontroller unit, you would wire this in from the PLC, and this would give you, here's your outputs from your PLC, and then you go through 2K resistors, and those would be your pulse, your drive action, and your enable switch on the stepper motor driver. Okay, so that would be your signals: direction, enable, and pulse. You would set this up. It tells you here how to set it up. You have to set the bits up on this one. You have to at least do this. Read through there. Try it. See if you can get it to run. It should run with the application program that we have for the eval board and the stepper. It should run. It should take off and work correctly, and it does. Here is where I was talking about before. This is where you would actually do the converting of a program from one processor to another. So if you are doing revision levels only, 1214 to 1214, that works, and you can just, it will automatically go to the next revision level. But if you're converting from a 1214 to a 1215, for instance, you would have to do this application, which is under View. You would create a reference project and bring in your reference project, and then bring your new project, basically change the model, and you can do that under this one. You can bring in a reference project, then change the model number here, and you can actually drag all the parts and pieces of a 1214 program in and put it into a 1215 if that's what you need to do. But this is these are the steps to do that, and I've had to do that in order to get it to run. Okay, so we're not going to go in depth into any of the other programs, the Allen Bradley Step or the Allen Bradley Servo or the Siemens Stepper, but at least this gives you a little bit of a heads up as to getting started with those. And like I said, the starter programs for each of these are on the web at the bottom of my website, and you may get started with either or both, or really any of the three of the old eval board for the stepper, the new the robot shop version, the one I just showed you in chapter 19, or the servo, which is chapter 20. Take care and have a good day. Hi, we're looking at chapter 19 of the lab book, which accompanies chapter 17 of our text. And we're talking about a stepper using a specific motor, and this is the kit that you would have found in one of those kits that we have in the lab. And this is purchased from Amazon, a number of different sources, and
we basically take this motor and we take the controller and we tie it to a stepper output from the Siemens processor, and we turn a stepper motor with it. So they talk about in chapter 18 of the labs the prior motor. This is the second one. This would be the chapter 19 motor. And in chapters 18 of the lab text, they talk about specifically turning on and off some dip switches. Well, we're taking those dip switches and we're moving them to an HMI panel. And we're going to allow the HMI panel to do the same thing. So instead of doing these dip switches, we're actually going to move these into the to the panel. We'll describe how that's done. This program is already given to you. It's on the web. It's the starter for the motion from Siemens. And you may have to do an upgrade of the version level, but that probably is about all you have to do. And the program is already set, and the outputs are already set. The pulse output is in Q0.0, the direction is in Q0.1, and everything else is pretty well done. Now the wiring from Arduino or a small microcontroller is listed here, but we show you the same inputs from the Siemens, and this would be the Q 0.0, 0.1, 0.2, and you have to put these 2K resistors in, and then you would wire to the interface module, and then from the interface module you'd wire to the stepper. And you need 24 volts to the from a power supply, and do not go through the Siemens LM feed. Go straight from the power supply to the ground and the VCC. It's important. It's also important that you turn off the stepper motor controller and the power when you're not in use, because there's a lot of power that goes through these, and it'll eventually get them hot and they'll eventually die. So when you're done, turn them off. The dip switch settings are here, and suggested dip switch settings are listed here at the bottom of this page. So from the dip switch table, be sure to turn off at least one of the first three. And to start, turn the switches S1 to on, S2 to on, S3 to off, S4 to on, S5 to off, and S6 to off. And from there, you can try other combinations if you'd like, but that's a starting point. This is the specification for the motor, and we see it's 2 amps, or it's 1.7 amps. So we set it at 2 amps maximum through the controller, and we're all set. So here is the graphic on the 17HS4401 stepper motor. Okay, so we really don't have to do the commissioning. It's already been done for us, but I at least showed you that as a page. We're going to go down here real quickly, and if you have to upload a program from a different processor, in other words, a 1214 to a 1215 or vice versa. I'm using this on a 1215, but when I did it, first of all, I had to do this screen so from a reference project. So if you're going from a 1214 to a 1215, in a project like this, you really do have to use this block and do the reference project and then drag it in from there. So it's pretty easy, but you have to know that window exists. So again, be careful as you do this so that you get it correctly done. Okay, so here is the program in the program controller. And I want to review it for you for a couple of minutes. And then we're going to go through and we're going to go online. And then we're going to bring up the HMI panel. I'm going to show you how I did the HMI panel. So instead of the way that it was done in the one that you're given on the web, I changed these bits from I's to M's. So tag 1 is an M 0.0. That is your reset. The power is tag 2 and it's M 0.1. So I address these to internal M bits because I'm going to tie them to bits on the screen. The next one is the homing bit, and that's M 0.2. So tag 3 is tied to M 0.2. Tag 4 is tied to M 0.3, and that's a velocity block.
and I did not use anything with velocity block. I did not put a variable there for the velocity block. You can do that if you want to. The move relative, which is the one we are using in this demo, tag 5 is tied to M0.4, and we put variables in there called distance relative and velocity relative, or distance R and velocity R, to tie these to variables that then we can change in our HMI program. Halt is M0.5. Move absolute is position A, and velocity A, absolute, and tag 7 is tied to M0.6. So those are our bits in our program. Now I'm going to go down to our HMI program, and I'm going to bring up our screen. So we've created a screen called Screen 1. And Screen 1 has these buttons: reset, off, and on. So this is a switch, this is a button, 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 and this is a button. So basically I programmed these as buttons like you would push a switch, like you'd push a push button, and I'm going to go down and I'm going to show you how they're set. So for reset, I set it as a button, and under events I did press, and set bit while key pressed, and the tag is tag 1. And I did it for all the rest of them as well. Now this second one is a switch. It's this guy right here. So this is a switch. This one is a switch, off and on. And then you set the event to a function. Really all I had to do here was tie it to tag 2, and that was all I had to do. Home is a push button, and again, it's on an event, and it's tag 3 under set bit while key pressed. Move, again, we're not using move, but it's set under a button. And relative move is also under a button, set bit while key pressed, tag 5. And over with that, I have these two input I/O fields, and this one is the one for the amount, how long it goes, or how far it moves, and this is the speed. So this would be the motion, the relative motion, and this would be the speed. We're going to play with those. And then the halt would be the halt, and the text, and the last one was we didn't use. So anyway, we're the text one was the table, which we did not use. So we're going to compile the PLC program is already downloaded, so we're just going to go back to the PLC program. We're going to go online. And we're going to go with the glasses so you can see it. You can see these bits, and if you want to, you can actually see it as it works and all that sort of thing. But I'm going to go to the HMI program. And I'm going to click on it, start simulation. It's going to take a while. It'll come up. It's working at it. So here we are. Kill that second one. Here's our program coming up, hopefully. So you'll hear it, and then later on I'll show it to you. It's hard for me to do both. So let me do it with this simulator first, and I'll move this over to the side. And okay, I'm gonna move this over to the side, and I'm gonna go back up to my program, my main program. I'm gonna go to a watch table, which I've built a watch table for, watch table 1. My variables are in there, and I'm going to now come back to my program, and I'm going to click on, and then reset, which resets the drive, home, which homes the drive, and then I've right now got a position of 1,000 moves and a relative speed of 20, and I'm going to click on this. You can actually hear it moving. So I may not want to go quite that many steps. Oops. I'm going to halt. That off. That'll turn it off. Okay, turn it back on again. So I'm not going to quite that many steps. Let's go 200 steps. 200. Do it again. Let's go with a little bit different speed. Let's go with 50. And click relative move. So now I have a move of 200 increments with a speed of 50, and I'm going to go to the other, we're going to watch this physically move. So I'm going to go to the other screen and pick that off and see if you can see that. So it's going to take us a second here to get set up. So let's try that. And we're going to go to the video capture of this and see if we can get that working. So here under video capture, yes, and I'm going to go to my video capture device, which is this, and there. Oops, I got the wrong one. I got to go this one. I got to go to the other one, and here we are, and there we are on the screen. And I'm going to put this right here in the middle so you can see it, and I'm going to transition over to you. And now when we do this, I'm going to describe to you what's going on, and you're going to be able to see it physically go. So I'm going to go relative move. Okay, that's move of 200 with speed of 50. Let's go with a speed of 100 and see what we can do at 100. Let it rip, huh? So that would be a total revolution at 200 at a speed of 100. We want a chance a little higher speed. Let's go to 200. See if it works. May or may not work. Let's try it. Didn't work as well, did it? But it kind of worked. But anyway, we may be gone too fast for the speed of this guy. So again, we want you to understand the physical aspects of it and also the software aspects of it, but you can at least have an idea how this thing works and how we're setting it up and trying to make it work. So look in those applications, and we'll in those tubs, and we'll set this up. Don't forget the resistors. Don't forget to set it to 2 amps or less. It's 24 volts that comes straight from the power supply. Wish you the best.